Hi friends, welcome back to Wikipedia World. Today we will be starting a new chapter which is Thermionic Emission and Radioactivity, and today's lecture will be focused on the first part of it, that is Thermionic Emission. We'll start by studying the introduction, understanding what is bound electron and what is free electron. After that we'll see work function, what is it, what does that mean, and finally the last topic of the discussion today will be thermionic emission. We'll understand what is thermionic emission and how does it manifest using a simple experiment. So let's start with our discussion on thermionic emission. In order to understand the concept of thermionic emission, we first need to understand how are electrons distributed in an atom. So if you have read it beforehand, you must be knowing that the distribution of electrons is such that the electrons are distributed in outer shells, whereas the proton and the neutron is at the nucleus of an atom. This is something like this. So here is my nucleus and this has my proton and the neutron, and we have shells surrounding this. Okay, which has electrons moving. The exact distribution I will not show here, but there are defined paths on which electrons move, right? And since an atom is electrically neutral, the number of protons inside the nucleus, which are the positively charged particles, is exactly equal to the number of electrons revolving around the nucleus. Why so? Because the charge of a proton is exactly equal to the charge of an electron, just opposite in sign. Okay, with this background, let us understand what are bound and conduction electrons. Bound and conduction electrons. Now we have seen that electrons move in different orbits around the nucleus. So this orbit is closest to the nucleus, then there is this orbit which is a little further, then there might be another orbit. So there are multiple orbits in which the electrons are distributed, right? The electrons which are closest to the nucleus will be closest to the proton, isn't it? And as a result, they will have maximum attraction for each other. Therefore, the electrons which are close to the nucleus will be highly attracted by the nucleus. Those which are further away from the nucleus will not be attracted that strongly to the nucleus. Thereby, the electrons which are close by are not free to leave the atom, as in they are tightly bound at their respective orbits. Such electrons are known as the bound electrons. Okay, because they are bound with the nucleus. Now, what are conduction electrons? As I said, there are multiple orbits in which electrons revolve around the nucleus. Now, there will be an outer orbit in which there will be certain electrons. These electrons are very lightly attracted by the nucleus and they are kind of free to move. What happens is when there are a number of atoms, when there are a lot of atoms, then the outer electrons forms a cloud which is known as conduction electrons, and they are separate from the atom. Okay, and they are free to move around in the whole material. So they are known as conduction electrons because they are free to move. They are also known as free electrons. Free electrons. So the outermost electrons which are free to move throughout the material are known as free or conduction electrons. Okay, now what exactly does this imply, or how does this implement itself? The metals which are known to be good conductors have a lot of free or conduction electron, thereby they are good conductors, whereas insulators which are known to be bad conductors do not have free outer electrons. So they do not have any free conduction electrons, thereby their conductivity is quite bad. Insulators have almost every electron as a bound electron. Okay, so that is how the bound electrons and the conduction electron manifest itself physically. Now, as I have said, that the conduction electrons or the free electrons are free to move throughout the body. Suppose this is a metallic piece which has many electrons, some maybe 10 to 20 atoms, thereby much more electrons than that, and those atoms will provide free electrons which are free to move, right? But these free electrons are free to move within the body of the metallic conductor. But these free electrons are not free to leave the body, isn't it? Because they are still held with the whole atomic system. But if we provide energy externally to this body, metallic body, by let's say maybe heating, then what will happen is you will end up getting free electrons in the real sense. That is, this electron over here can leave the body, and that leads to emission of electrons. So emission of electrons, this is basically emission of free electrons, and this takes place by providing external energy. So what exactly happens in the process of emission of electrons from the metal surface is that the energy is absorbed and the electron gets emitted out of the body, right? Now, why does this happen? This happens because the heat which we are supplying to the body will lead to an increase in kinetic energy of the electrons, and when the kinetic energy of the electron becomes sufficiently large, it will be able to overcome the attractive forces from the atomic bulk and leave the system. Now, how much energy is exactly required in order for the electron to be emitted? This is defined by what is known as the work function. Work function. Now, work function is a material property. What this means is that the work function for a particular material will be always the same for that material, and it will be different for different materials. Work function is the minimum amount of energy that is required to emit electrons from a metal surface. Okay, so it is minimum amount of energy required to emit electrons from a metal surface. So what this means is that larger the work function, more will be the energy required to emit electrons. Smaller the work function, less will be the energy required to emit electrons. Normally the work function as you can see, it is a unit of energy, but the work function is normally defined in terms of electron volt. That is how much electron volt is required to emit the electron. That is a more convenient way to express the work function. And as an example, I will show you couple of elements work function. Tungsten, for example, is 4.52 electron volts. So for a electron from tungsten body to be emitted, it requires 4.52 electron volt. This is quite high work function. On the other end, potassium, for example, has a work function around 2.26 electron volt. So potassium requires almost half the amount of energy to emit one electron compared to tungsten. Okay, you can find the standard values of work function for different metals or different materials by doing a simple Google search. You will get all the results. I'm not going into details about each individual element, but the take home point is that every element or every material has a specific standard work function which is unique to itself. Okay, now that we have seen what is work function and how exactly does the emission of electron takes place, let's see our point of discussion of today, that is thermionic emission. As the name suggests, therm refers to something related to heat and ions is charged particles, emission is emission. So basically, if we provide emission of electrons by supplying heat as the source of energy, then the emission of electrons in such a case is known as thermionic emission. Okay, so the emission of electrons from a metal surface when heat energy is imparted to it is basically thermionic emission. Now I will discuss an example of an experiment which was carried out by Edison to discuss thermionic emission. Let's do that. So what he did here was he took this filament and he applied a huge potential difference by a battery across this filament. Since this is a filament, this leads to a current flow here, leading to heating up of the filament to very high temperature, and that heated up filament is the source of energy, right? Now this will result in what is known as thermionic emission, and we'll see that in details now. Now he carried out two scenarios. In one scenario, what he did was he connected the positive terminal to the spare filament. As a result, what happened? This turned out to be a positively charged section, and when electrons were emitted from here due to the high potential energy from the battery, then the electrons were attracted by this positive charge here and they went and attacked here. Okay, and that led to completion of the circuit, and the galvanometer showed reading movement, which means there was current flowing through the circuit. Okay, a point to note here is that at that time when the experiment was carried out, the concept of electron did not exist. We did not know that electron actually exists. What Edison concluded was that some negatively charged particle is being emitted. Okay, because only then it is attracted to the positive terminal. Now in the second case, what he did was he switched this switch from the positive terminal to the negative terminal. As a result, what happened? This spare filament turned to be negatively charged. Now when this became negatively charged, then the electrons though were generated here, but since it was negatively charged here, it was not attracted towards this filament. as a result, electrons did not flow and there was no deflection of the galvanometer, resulting in no current flow, which explicitly meant that the charged particles which are generated from here were negatively charged, because in the case of positively charged particles the circuit became complete by it being attracted to this end, whereas when this is negative, since this is the emitted particles were also negative, it was not attracted to this end, rather it was repelled and the circuit was not complete. Okay, so this was the simple experiment carried out by Edison, which proved that when a source of power is applied, then negatively charged particles are emitted. Now in 1897, Sir J.J. Thomson found out that there are negatively charged particles in atoms which are known as electrons. And once he found out that, then that was connected with this experiment here, and it was understood that the particles which were being emitted were electrons, right? And with that, this process was termed as thermionic emission, and the particles being emitted were named as thermions. Why? Because what is happening here is this is the filament, and this battery is leading to the heating of the filament, and that heat results in the emission of electrons. So basically what we see is electrons are being emitted by the heated filament. Fine. So now that we know what is thermionic emission and why does it take place, let us see what are the factors which affect the thermionic emission. One important factor is the nature of the metal surface. As we have already seen, the work function depends on the nature of the material. So obviously the amount of thermions emitted will depend on the nature of the material being used. Secondly, the temperature of the surface. Higher the temperature attained by the filament or the surface, more will be the number of electrons emitted, because then there is more energy available for the electrons to be emitted. Finally, there is the factor of surface area of the metal. Given that the temperature and the work function is the same, more the surface area exposed, more will be the number of electrons being emitted. Okay, so these are the factors on which thermionic emission depend. Now let us see what are the prerequisites of a very good electron emitter. So the prerequisites would be: one is low work function. Lower the work function, less will be the energy required for electrons to be emitted. And second is high melting point. High melting point. Why is this important? Suppose you have a material which has low work function, relatively low work function, but very low melting point. When you start heating it, instead of electrons being emitted, before that the material might melt, and then it is not a suitable material for thermionic emission. So we ideally need to have a high melting point so that the material remains intact, and low work function so that less energy is required for electrons to be emitted. Okay, now with this idea, let us see some of the materials which are practically used when thermionic emission is required. If you think about tungsten, as I have already mentioned here, tungsten has a work function of 4.52 electron volt. This is a little on the higher side, but a point to note is that the melting point of tungsten is also quite high. The melting point of tungsten is approximately 3655 Kelvin. Therefore, the high melting point criteria is met. The low work function is not exactly met, but it can be used for practical purposes. But again, there is some simple modification in the tungsten which can lead it to be a much more effective thermionic emitter. What is so? Suppose that instead of using pure tungsten, you use thoriated tungsten. So basically thoriated tungsten is tungsten coated with carbon and thorium. Let me write it down. Thoriated tungsten. What this does is the work function is reduced to 2.6 electron volt, and under such circumstance, even at 2500 Kelvin, electrons can be emitted. Thereby this is much lower than the melting point of tungsten, and this is a good choice for thermionic emitter. Okay. Alternatively, rather this 2500 is the emission temperature for tungsten. For thoriated tungsten it is 2000 Kelvin. So we see that 500 Kelvin drop is there. Now what is the other alternative is to coat tungsten with barium, cesium or strontium oxides. These oxides have very low work function of their own. Therefore that results in a total low work functioning reduction in total work function of the combination. And if we use this barium, cesium or strontium oxides coated on tungsten, then its work function is around 1 electron volt, and electrons can be emitted at around 1000 Kelvin. Okay, so this we see that drastically reduces our work function and the temperature at which thermionic emission can take place. This is a very practical combination of material that can be used as a thermionic emitter. Okay, so this brings an end to today's discussion. What we saw today is we started with the concept of bound and conduction electrons. We saw what is work function, and then we saw Edison's setup where we saw how electrons are emitted by a heated filament. An important note here is that this battery creates a potential difference, but it's the potential difference at the filament leading to the heating of the filament to high temperature that is leading to electron emission, hence thermionic emission. It's the temperature of the heated filament. Okay. After that we saw the properties which is required for a good thermionic emitter, and we saw a couple of examples of good thermionic emitters. Next class we will see what is a hot ray cathode tube. Till next class, have a great day. Goodbye.